Welcome to lecture 33 of MCS 471 on numerical analysis. So today we start a new chapter. We consider boundary value problems. These are ordinary differential equations where instead of specifying conditions at the beginning, we specify conditions at the boundaries. So we will see how to reduce a boundary value problem to the initial value problem via shooting. So the method of shooting is the main subject of today. We will in later lectures, we will consider finite differences and finite elements. So we have 3 lectures on the solution of boundary value problems. We will reduce the boundary value problems via shooting to initial value problems, and we will apply interpolation and numerical root finding via interpolation. So in a way, we reduce the methods that we know already. So we reduce the problems, the new problems, to old problems for which we have already methods. So in the first part of this lecture, we will be introducing the main technique of shooting. And then shooting reduces to 2 initial value problems in case the problem is linear. In case the problem is not linear, then we will need to shoot multiple times and we will apply higher order interpolation. So this will be illustrated with the model, with the simple module of the pendulum. So we will see the pendulum problem as a nonlinear boundary value problem. All right, let us start with a simple example. So we consider a falling object where we start from an initial height of 30 meters. So that's the initial condition. And we will try to, so the initial condition is y0 equals 30. So that's the initial condition that is here, y0 equals 30. And then we have a differential equation. So every object is subject to gravity. So we have a second order differential equation. Turning this into a boundary problem means that we want to set up this model so that at time equals 4, the height equals 0. So that's the second condition. So that's we consider the time interval from 0 to 4. Initially, we start at 30. At the end, we end at 0. So we consider this boundary value problem. All right, this is essentially a simple boundary value problem because the right-hand side is a constant, so it is a gravitational constant. We can solve this problem symbolically by integrating twice. If we do this, we have 2 constants that come in. The first constant that comes in is the initial velocity. So we have our velocity, that is the first integration constant. The second integration constant is the initial position. So if we have the 2 conditions, so how can we solve this simple problem? We have 2 conditions and we can solve for the velocity using the boundary value problem, using the condition imposed by the fact that at t equals 4, our object has to be at level 0. So that gives us the initial velocity as 12.12. So because the right-hand side is a constant and we have a second order, the solution is a quadratic polynomial with the three constants, the gravitational constant as the acceleration, the initial velocity as the term with t, and then the constant term of our solution is the initial position. So here is how symbolically we can solve this boundary value problem very quickly in case of a constant right-hand side. In general, we will consider order 2 boundary value problems. Order 2 means that we consider second order conditions, second order differential equations, and we have two boundary conditions. So in general, we consider the interval from A and B, and we impose two boundaries conditions. So for today, we will reduce this problem to an initial value problem. But there is a problem though. We must know the initial velocity, and we do not know the initial velocity. But we will do it anyway. So we will guess the initial velocity, run the initial value problem, and then adjust the initial value problem. So we will reduce this to a root finding problem for which we do have a backward problem. So in a way, boundary value problem solving with shooting will be equivalent to solving a nonlinear equation or a linear equation in case the boundary value problem is a linear problem, as we will encounter. So here is the general idea. So what we are computing is a trajectory, so here displayed in red. So we have a solution trajectory going from A to B, and suggesting that what we need to turn this into an initial value problem is the initial velocity, displayed here by the blue vectors. If only we knew the initial velocity, then we can apply our techniques that we have covered in the previous chapter for solving initial value problems. So, but we can turn this into an initial value problem by guessing, by imposing, by assuming an initial value for y prime at the left of the interval. That is what we're going to do. So the y prime bar, so the overlined, is our initial guess. And here you see that with this initial guess, we obtain an end value. So we are computing a new trajectory, so the overlined y, and we can check at the end whether our end position at B corresponds to the condition from the boundary value problem. And here you can see by looking at the picture that we have undershot. So our velocity or our angle, our initial angle of the trajectory was too low. So I hope the pictures illustrate the name of the method. So you can see this as a problem of artillery, where you try to aim your cannon, so the slope of your cannon, so that you will hit the target. So the target is here the end value for the end, the value of the solution trajectory at B. So we undershot, so let's then take a larger angle and solve an initial value problem again. So now you see with the picture that our angle was too steep and we ended up too high. So one can see this again with the initial problem that we started with the falling object. If we give it an initial velocity that is too low, our object will hit the ground too soon, or if we give it an initial velocity that is too high, we will not hit the ground at time equals 0. All right, so this is a method that is kind of absurd with a lot of trial and error, but we can learn something from our mistakes. So after computing two trajectories, we can be a little bit smarter to get a next big guess. One initial trial that the next trial we could do would be to average. We could try to do something like bisection. Bisection is a good method, but we can improve on that. We can do interpolation. And that's what we will apply when we run the shooting method. What is the setup? So for the initial velocity, we tried two values. So here we call them capital Y and capital Y1 and capital Y2. We obtain two different values for the end. So function value capital F1 and function value capital F2. So we can now say that with every, so suppose that the problem is well posed, so we have a unique trajectory, a unique solution to every initial value problem. So there is a function that exists that if you are giving that function on input a velocity, you have a unique position on output. So that's that unknown function f, capital F, and we have two data points, F1 and F2. We can now predict what the outcome will be if we are giving it any velocity. We can interpolate. So if we are assuming a linear relationship between the velocities. So if we are giving it a lower or a higher velocity, we will get closer or less, or closer to one of the values or closer to another of the values. We construct the interpolating polynomial and we can apply Lagrange. You can see that from the formulation, if y, capital Y equals y2, then the first term disappears and P takes the value of F2. If the Y equals Y1, then we have that our interpolating polynomial takes the value F1. What does this help us? Well, we have a linear equation. So here is where interpolation helps us. We will set this equal to YB. So we want to compute that value for the Y so that we obtain, so we are looking now to solve a linear equation. So the problem after two trajectories is now computing the value for the initial velocity so that at the end we are computing the end value. So our interpolating polynomial models the outcome of giving an initial velocity. and we want that the input is a velocity, the output is the value at the end of the trajectory. Let's apply this. So we have an initial, a boundary value problem. We have computed two initial value problems, constructed an interpolating polynomial, and we are computing the next guess for our velocity as the solution of a linear equation. So the linear equation expresses that at the end we must find the second boundary condition. So that's simply solving a linear equation. So the y3 here will be the initial velocity for our initial value problem. It will turn out that if our problem is a linear problem, then we actually don't need to compute anything else. So a linear problem we can solve with two initial value problems. So let's show this. So what is a linear problem? A linear problem has only constant coefficients. So we have a general form for a second order differential equation. So you see the double prime, single prime, and the y. We have three coefficients, capital F, capital G, capital H, and these coefficients do not depend on x, do not depend on y. If that is the case, then if we have any two solutions that are distinct from each other, then any linear combination, and the linear combination is kind of a weighted combination. So we are combining the solutions and dividing by the sum of the coefficients, then that is also a solution. Let's verify this. So if we plug in the linear combination, so we have the linear combination of the two solutions here, we plug it in into the differential equation. And you can see that by regrouping and by using the fact that y1 is a solution, so if y1 is a solution, then this gives h. If y2 is a solution, then we have h2. And we now see why we have to divide by C1 plus C2. Otherwise, without this, we would have a right-hand side that is a linear combination of H. That is a C1 plus C2 times H. We would obtain a multiple of H. If we have a pair of two solutions to a second order differential equation that is linear, then we can build the whole family of solutions. So we have the two constants that parameterize that entire family. So this is more general than we started with our first equation, which had only a constant right-hand side. All right, so if we look into assuming now that we have our falling object problem, if you have a problem like that with a constant right-hand side, then we can compute the exact solution. But this is a very good test problem to compute to exercise with the method of with the shooting method. We know the exact solution. So in practice, we will run a numerical solver, but here one can solve this problem by just plugging in the initial values. So we will run the initial value problem replacing the constant, and here you see if you want to solve this. So the 12.12 is the exact velocity, but you will replace this by 10 and see what you get if you evaluate then this function, and you will also do it with 14. So after that, by linear interpolation with the shooting method, you should find the 12.12 as the correct initial value. All right. Second question, second exercise is to use the Runge-Kutta 4-5, so the embedded pair of Runge-Kutta methods of the integrate module of SciPy on exactly the same problem. But now you will compute the interpolating polynomial with the numerical values that you obtain for the end position. So with y1, you get a value for y4. With y2, you get a value for y4. Again, you will see that the initial velocity y1 is too low, so the exact velocity is 12.12, and you will end up with a negative number. With y2, initial velocity 14, which is higher than 12.12, you will not be at level 0 of your falling object. So you will obtain a positive value at the end. So you can see how the bisection method would apply here as well. So one can then take the midpoint between 10 and 14, which is 12. But if you apply linear, if you apply interpolation, you will find 12.12. The difference between exercise 1 and exercise 2 is that for exercise 2, you apply the numerical computation. So let's continue with this. One distinguishes between boundary value problems where one gives the positions as the conditions, and one can also provide the derivatives as the boundary conditions. So we call them Dirichlet and Neumann conditions. So we started out by imposing values, conditions on the endpoint. So they are called Dirichlet boundary value problems. With Neumann conditions, one imposes conditions on the derivatives. So we know at the endpoints of the intervals what the rates of changes are, but we do not know the initial values. So in some sense, in applying the shooting method, then it's less intuitive. So you actually know the slope of your cannon, but you do actually not know where to position your cannon. So that's an alternative, a way of applying the shooting method. Instead of changing the angle of your cannon, you are going to change, you're going to keep the angle, but going to move your cannon more forward or backward. So one can interpret the solution of Neumann boundary value problems as keeping the angle fixed, keeping your velocity fixed, but changing your position. So there is a geometrical interpretation also. All right. So the shooting for Neumann conditions is here summarized again in 3 steps. So we will first solve 2 initial value problems. And it's important to work systematically. So we will use symbols F1 and F2 as the values for what we obtain by the end. And then we construct the interpolating polynomial and solve. So it's not a root finding problem, although it is, but you have to subtract the value, the derivative, the desired derivative that you want. All right, so this is the Neumann conditions. I'm sorry, so with the Dirichlet, we had at the end values f1 and f2 were the non-primed symbols. Here the difference, and perhaps I will mark it now, so it's the very same method, but we have a prime, so prime in two cases. But it is the same shooting method. The meaning of the symbols changes. The capital F1 and the capital F2 with Dirichlet problems were the values that we obtained as the solutions of the initial value problems, which were the values for the positions. Here with the Neumann conditions, we obtain values for the incoming, for the angle of approach at the derivative at the endpoint. And we will apply interpolation again. Here is a problem where we have mixed conditions. So this is no longer a boundary value problem. And in these type of problems, what the equation is doesn't really matter to explain the technique. So we have the interval AB from 1 to 3. We have two boundary conditions, 1 and 10.01. And our F1 and the F2 are actually now the obtained values for the derivative. We turn this into an initial value problem, estimating, so our first value was 1, we try 2 for the position, and we obtain then a velocity. So why is this now mixed condition? Well, we have a guess for the initial position, and we obtain a value for the derivative. So we know in this problem what is the initial velocity, but we actually do not know the initial position. So we can still talk about over and undershooting by comparing to the given value for the derivative at the end of the interval. And again, we could apply bisection. I'm referring to bisection because that's the solution of the textbook, but the interpolation is much more accurate and actually much more general. So if this is a linear problem, then solving this equation here, so solving this equation for the value that is here a given, so that's the value that we have to solve for. So py has to be equal to 10 for this value here. We will obtain then the correct solution. So this is what we do. So here is what the equation is. So the equation is the value of the interpolating polynomial must equal the value at the end, which is the value at the end is here the derivative. So this is solving a linear equation. And we will take that as the root. Here is a sanity check. In one case we undershot, in the other case we overshot. And you can see that we took 1 and 2 as the two values. So we have to find something in between if we have an undershooting or if we have an overshooting. It could also be that in both cases we undershot. Then as a check, the value that you find must be larger. So there is this natural proportions between the natural relationship between the values. All right, here is another example. So here we have our second boundary value problem with the right-hand side that is equal to y. So this is again important to see what type of problem is this. We have a constant term. So remember the general form of a linear problem. We have a linear problem y double prime plus f times 1 prime plus g times y equals h. Here the f in this general formula, so let me try to indicate that it's very important here that when you see a second order equation that you can distinguish between a linear and a nonlinear one. So the general form was that we worked with constants f for y prime and g for y, and the right hand side was h. So both these three constants, f, g, and h, were independent from x or y. So the problem y double prime equals y is corresponding to g equals -1, h equals 0, and f also equals 0. So this is a linear problem. So it is a von Neumann problem or a Neumann problem because we are given a boundary value problem with values at the derivatives. So we do know the initial velocity and the end velocity. We do not know the initial position and we do not know the end position. So running a solver to this problem leads to an undershooting and an overshooting for the value of the derivative. And we can obtain the general solution now. So this is another way of solving this problem by exploiting the linearity. So what we will do is that we will solve for the constants C1 and C2. So we have two solutions. What these solutions are is actually not known, is not given to us here, but we can solve it for one particular point. So we know that we got at the end, we know what the constants should be. And we know what they are at 1 and at 2, at 3. We know we have the conditions, and then we can solve for the constants, which are here called gamma 1, gamma 2. We can solve for the y1 prime and the y2 prime. y1 and y2 now being the two solution trajectories that we computed. So with 1, we have y1 prime. So let me show how this turns into a linear system. So it's a linear system in the unknown gamma 1 and gamma 2. So we obtained for y1 we undershot, and for y when using 2 we overshot. So we have the coefficients in our matrix. So the y1 and the y2. So, and we can solve this problem because it is a linear problem. We can find the combinations of the constants. So if you have, so what is the conclusion here of this competition is that if we have solved two trajectories, and we can not only compute the next correct value for the missing condition, But if we have solved with an initial value solver, we have computed an entire trajectory, it suffices to do the combinations between all the values that we obtained using the gamma 1 and the gamma 2 constants. All right, very good. Nonlinear problems. So let us look at an example. So with a nonlinear boundary value problem, and this is where numerical analysis turned out to be extremely handy, there will not be any more a closed form solution as either. We now have, you can see that there is a derivative here, and the derivative, the constant in front of the derivative, depends on x and y. So we also have a function, a right-hand side function, depending on x. So this is a nonlinear problem. So for nonlinear problems, one needs to apply interpolation. Linear interpolation will often give a better solution. Sometimes we get one decimal place correct, but we need to continue this. We need to apply higher order interpolation. And I will try to explain this with the model of the pendulum. So in solving a nonlinear boundary value problem here, we will impose, so this is a problem that we reduce to initial value problem. It's a pure problem, so we do have conditions on the position, so it is a Dirichlet problem. We will guess values, so we will guess a value for y prime and solve an initial value problem. So by a guess for y prime at the beginning, we obtain an end value. So the end value should be equal to -1, but it will be a value that is different. So it will be essentially a bar value. So we predict the values. We can take 1, we can take 2, and then solve initial interpolation. So here we start, here is another boundary value problem. On the interval 0, 5, this is a Dirichlet problem. We do have the values that we obtained for y5 using 1 and 2 as the initial guesses. For the first problem, we will find, so this exercise has two parts. And to solve the first part, you set up the interpolating polynomial. So, and you solve that interpolating polynomial. So the equation is that P of y3, so you will compute y3, solving a linear combination so that the value equals 20. So that's the desired right-hand side with a guess for the initial velocity. And then check what you get with setting up the proper numerical integrator and compute the value for the endpoint. This is a nonlinear problem. It will be more accurate, and you should see that we undershot and we overshot. If you do not want to do interpolation, you could also do the bisection, takes the midpoint. But interpolation is actually more accurate. And we can apply quadratic interpolation, as I will try to illustrate now on the model of a pendulum, which is a second order equation. We derived that in an earlier lecture. It is a nonlinear right-hand side. You see the sine function. So the right-hand side is a function of y. It's a nonlinear function of y. We formulate this as a boundary value problem, imposing conditions on the input angle and the output angle. So our simulation interval is between 0 and 2 pi. At the end of the simulation, we want to arrive at the same angle. So starting the pendulum at rest, so no initial velocity with pi over 6, we find that so pi over 6 is a little bit less than 0.5, so it's kind of subtle. So we are here above pi over 6. Here we end, and you can see it, we have less than pi over 5, less than 0.5. So it looks like it's completely periodic, but there is something off at the end. So how do we solve this boundary value problem then? Well, here is the outcome. So there's a Jupyter notebook that is posted. And now you see that at the very end, we have, you can no longer see the difference, essentially. So what is here at the end, we have a value larger than 0.5, which is about the same as we have here. And you see that our initial velocity had to change. So the initial velocity here had to be kind of positive. So we need to give actually a positive velocity. So in this picture, you see that the red velocity doesn't start at 0. So that's actually the main difference here. That's quite noticeable in the difference between the two plots. All right, shooting with linear interpolation, we obtained in our initial trajectory, we have an end position at 0.4 instead of 0.5 something. If we give it an initial velocity 1, then that initial velocity is too high, and we end up at 0.6. So we overshot. How do we compute a better velocity? Well, we solve an interpolating polynomial. So you could say bisection, take 1/2, but we can improve on that value by applying interpolation. So in some sense, we are coming back to the root finding problem. We can formulate this as a root finding problem, and applying linear interpolation corresponds to applying the secant method. So the secant method is more accurate than the bisection method. And indeed, we find other value other than 0.5 by solving for pi over 6. So for which value in this linear function do we obtain pi over 6? It turns out this is 0.4.28. If you work with 3 decimal places accuracy. We compute the trajectory, so the numerical values on the slides are obtained by copying the values from running the embedded order 4-5 Runge-Kutta method. So for velocity, for the input velocity 0.428, we obtain an end position of 0.531. So the 0.5 is already correct here. We set up the quadratic interpolating polynomial. So verify that if z equals 0, then the second and the third term vanish, and the coefficient in the Lagrange interpolating polynomial gives us the value 0.4463. So Lagrange interpolation, which might have been kind of a far-fetched form actually now comes in very, very handy. So Lagrange interpolation is quite natural here to apply in this setting. Remember also the first computer project where we did Muller's method. So this is a variation of applying Muller's method for solving nonlinear equations. So we are solving a quadratic equation, and then we take the root that is closest to our last guess. So we have two roots. So if you would pick 5.3, which is kind of far out, we would obtain a solution that's completely wrong. But with 0.428, we still overshot the value of pi over 6. So we take a new value, which is 0.379. And that's the value that corresponded with the plot that was shown earlier. That gives already one extra and probably two more extra places of accuracy. So it's no longer distinguishable on a plot. So we did a simple model. We can consider the more advanced model. So here we have a more general second order differential equation that models a pendulum that has damping. So there is friction and there is also forcing. So we have a right-hand side now that is, so the constant B is actually, it's like now, instead of considering a pendulum that, well, that is swinging, so it might be more, so this model is more the model for pushing a child sitting on a swing. So here we solve the same boundary value problem here also with the two constants for A and B. Apply linear extrapolation and then apply quadratic interpolation. So extrapolation and interpolation are here used interchangeably because it could be that you, in both cases, you undershoot so that you get below the target value of pi over 6 by using, say, two low values for the initial velocity. Or if you take two large values, then you will, in both cases, overshoot your target. So the Jupyter notebook is a way to systematically organize your computations. So SymPy is very useful here. So on the slides, I did not include SymPy, but please check the posted Jupyter notebook for an application of SymPy here.